Hey calculus class, today we're going to learn topic 51, the logistic equation, and this is also a BC concept. Alright, so we're going to start off by watching this video that I found that I thought explained it fairly well.
Let's take another look at population growth. Now, we saw this a long time ago when we were looking at the exponential function, and we saw that if you think about it, the most simplistic but reasonable model for population growth is the following: that the rate of change of population with respect to time is equal to some constant times the population. And this makes so much sense, right? Because if you have a lot of people, or microorganisms all together, they tend to probably reproduce at a faster rate than if you had like 3 of them, right? The rate of reproduction would be a lot slower. So it's a very fundamental basic model and accurately predicts populations. But think about it. Can this really represent population long term? Now let's think about what that means. It means that the rate of change of population is going to be proportional to the current population, which when we solve the differential equation gives us exponential growth. Can we sustain exponential growth in real life? So constantly we're growing at faster and faster and faster rates, and so the population is growing exponentially. Well, no, that can't happen. That can't happen in a small town, it can't happen in a petri dish, and it can't happen on Earth. Because the bottom line is, if we wait long enough, then in fact there's going to be overcrowding, overpopulation, lack of food, lack of resources, and we'll start to experience death, and we'll get into trouble. So this is a great model if we're just thinking about short-term growth, growth over a small period of time. But long-term growth, we have to enter into the fact that we can only sustain so much because of limited resources, limited space, limited food, whatever. So, great model, but not realistic along the long haul. So how can we do better? Well, let's take a look and see how we can improve this simplistic model to create what's called the logistic model, which is a little bit better and captures the spirit that there are limitations to everything. We can't go on forever living in the life.
All right, so this introduces the idea of a logistic model, that we can't sustain population growth forever. So, all right, so let's look at a comparison between exponential growth and logistic growth. So with exponential growth, here's our typical graph. And with logistic growth, we have a graph that looks something like this, that it grows exponentially, but then at some moment in time, we have to level off. And we call that leveling, or y equals L, where L is the carrying capacity, the most amount of population that can be contained in that petri dish or on Earth or in the small town. So with exponential growth, it assumes that there are no restrictions on the quantity that's growing. Whereas with logistic growth, it takes into account realistic factors, the carrying capacity, which is the maximum number of species that a system can hold in the long run. In exponential growth, the growth rate is proportional to the population size. And in logistic growth, growth rate is proportional to both the population size and the carrying capacity. So the differential equation that we already know of for exponential growth is dp dt equals kp. And the differential equation for logistic growth is dp dt equals kp times 1 minus p over L. And keeping in mind that L is representing the carrying capacity. So solutions to the logistic growth differential equation. So let's look at an example. At Mount Rainier National Park, the carrying capacity for deer is 1,000 with a relative growth rate of 0.08 deer per month. So using our logistic growth differential equation, that means that our growth rate constant is 0.08, so I put that in place of little k, and our carrying capacity is 1,000, so in place of L. Now, the first way that you can approximate the solution for this logistic differential equation is with slope fields. So if I was to graph this differential equation as a slope field, I would get a graph that looks something like this. And what happens to the growth rate as the population of the deer reaches their carrying capacity? So as it's increasing, what is happening to the growth rate as it reaches 1,000? That means that dp dt, the rate of growth, is equaling 0, because we have, if you notice, little horizontal tangent lines, which means that the population is stabilizing. Now, what happens when dp dt is less than 0? That means that the population has exceeded its carrying capacity and is decreasing until it gets back to its carrying capacity. So that's up here where the tangent lines have a negative slope. So it's possible that Mother Nature is taking care of business, or there might be some hunters out there, who knows. Now, if we wanted to sketch the solution curves for p of 0 equals 100, and p of 0 equals 400, and p of 0 equals 1300, we would get 3 graphs that look something like this. Now, when is the growth rate the greatest? That is when dp dt is greatest at 500. Which is half of the carrying capacity, because that is where the slopes are the greatest. So if you look at the slope field, when P is 500, you will see that the slopes are the steepest right around here. This is also where the curve changes concavity. So there is an inflection point at P equals 500. All solutions that begin below 500 have the same inflection point. Now, another way that we can approximate is using Euler's method. So if we wanted to use Euler's method to approximate the deer population at certain times, then we would use our differential equation and our initial condition, which we're going to use as p of 0 equals 100. We're going to use a step size of 20 to approximate the population at 40 and the population at 60. And our time is in months, so 20 months, at 40 months, 60 months, etc. So our start is at 0, 100, and then our next months are going to be at 20, 40, 60. So we're first going to find the rate at 0, 100, which I get 7.2. Find the population at that rate, which is 244. Now I'm going to do it again using the new point. Get a rate of 14.757. Get a population of 539.142. And when you're doing this in your calculator, make sure you're storing the values. And then one more time, get a rate of 19.877 and a population of 936.691. So in just over 2.5 years, the deer population will meet its carrying capacity, right? Because we're pretty close to 1,000 here. So here's the analytical solution, which means the actual particular solution. So the logistic differential equation is separable, so we can solve by hand. So are you ready? We are going to need to use the following previous knowledge. We're going to need to use some absolute value, a little bit of partial fractions, lots more logs, and much more substitution. All right, so here we go. Just kidding. April Fools. Nope, it's 2 months early. I'm going to be really, really nice. It's long and tedious, so I'll just give you the solution instead. If you're super curious about where this solution comes from, the proof is on page 626 in your book. And you're welcome. So here's our solution. So the initial value problem for logistic growth, given the differential equation and a starting population, has a particular solution of P of t equals L, the carrying capacity, over 1 plus A times e to the negative kt, where A is equal to the carrying capacity minus the initial population all over the initial population. So we have that P naught is our initial population at t equals 0. K is our relative growth rate. T is the time the population grows. L is the carrying capacity. And P of t is what the population grows to after some time t. All right, so now back to our deer problem with the differential equation. Now let's go ahead and write a logistic model that represents the deer population at Mount Rainier National Park. So first we need to find A. So our carrying capacity minus the initial over the initial, which reduces to 9. So that means that my particular solution will be P of t equals 1,000 over 1 plus 9e to the negative 0.08t. Now we're going to use P of t to calculate P of 40 and P of 60 and compare these values to the approximation that we got from Euler's method. All right, so I'm going to plug 40 in for t to get 731.604. Now I'm going to plug in 60 for t to get 931.040. And when we did Euler's method, at P of 40, we approximated it to be 539.142. And at 60, we approximated it to be 936.691. So Euler's method was not too far off from the actual P of 60, but of course we would have gotten a better approximation if we used a really small step size. All right, so what is the value of the limit as t approaches infinity of P of t, and what does this limit mean? So I'm going to take the limit of my logistic growth model. When I plug infinity in, I'm going to get an e to the negative infinity. And as the exponential graph is approaching x values really, really small towards the negative direction, we are approaching 0. So that means that our limit is going to be 1,000. So as time moves on, becomes greater, your population approaches the carrying capacity. So in the long run, the population approaches its carrying capacity. In other words, the population becomes stable at its maximum capacity. At what deer population does the rate equal 0? So that means I'm going to set my rate equal to 0 and solve for P. And so when I set each factor equal to 0, I get that P will equal 0 and P will equal 1,000. So the solutions P of t equals 0 and P of t equals my carrying capacity are what are called the equilibrium solutions, because the population must stay at this value. All right, let's try an example. A 2,000-gallon tank can support no more than 150 guppies. 6 guppies are introduced into the tank. Assume that the rate of growth of the population is dp dt equals 0.0015p times 150 minus p, where t is in weeks. Find a formula for the guppy population in terms of t. Then determine how long it will take for the puppy population to be 100. All right, so here is our differential equation. And notice that it doesn't quite exactly look like our logistic growth differential equation because we're supposed to have a 1 right here. But I can make this one by dividing by 150, since that is my carrying capacity. So now I have, so far, for my P of t equals 150 over 1 plus AE to the negative 0.0015t. And I need to find A. And I know my initial is 6 guppies. So that means that the A value will be my carrying capacity minus the initial over the initial, which reduces to 24. So that means my particular solution for the amount of guppies is 150 over 1 plus 24 e to the negative 0.0015t. So I want to find how long it's going to be for there to be population of 100 guppies. So I'm going to set my population equal to 100, and I'm going to solve. So to do that, I divided both sides by 150 and reduced the fraction to get 2/3. Then I cross multiplied, subtracted the 2, divided by the 48, natural logged both sides, and divided by that relative growth rate constant. And then to get the approximated value for t, it will take approximately 2,580.801 weeks. All right, why don't you go ahead and try this example on your own. All right, let's see how we did on this highly contagious pink eye that is ravaging the local elementary school. So there is 900 students and staff in the population of the school, and the rate of infection is proportional both to the number infected and the number of students whose eyes are pus-free. So right there it tells you that this is logistic growth. If 75 people were infected on December 15th and 250 have contracted pink eye by December 20th, how many people will have gotten the gift of crusty eyes by Christmas Day? So our carrying capacity is 900. So that means my beginning of my population logistic growth model is the following. And the starting amount of people that were infected is 75. So to get A, I'm going to take 900 minus 75 over 75, reduce it to 11. So that means that P of t will equal 900 over 1 plus 11 e to the negative kt. Now our goal is to find P of 10 because we're starting at December 15th and we want to know how many people will have gotten the disease on Christmas Day, which is December 25th. So that's 10 days have gone by. But in order to find P of 10, we first need K. And if you notice, we've also been given how many people have gotten the lovely infection 5 days later, which was on December 20th. So we're going to use that when T was 5, the amount of people with pink eye was 250 to help me solve for K. So to do that, I divided both sides by 900 and reduced the fraction. Cross multiplied, subtracted 5 from both sides, divided by 55, natural log both sides, divided by negative 5. And if you put that in your calculator, you would get a pretty long decimal, so make sure you store that in your calculator. So now since we have K, we now actually have our logistic growth model. Now we can find P of 10. So now I can put 10 in for T and simplify it to get 557.432 people out of the 900 will have gotten pink eye by Christmas Day. All right, let's look at this example. Tom can bench press 200 pounds today. Because of Tom's size, he can only bench a maximum of 250 pounds. When Tom started working out 3 years ago, he could bench press only 50 pounds. How much could he bench last year? So we have our maximum possibility, which was 250. So that gets us a start on our our logistic growth model. And I know that it's not population. You can use a different letter if you don't want to use P. And our start, when he started working out, he could only bench press 50 pounds. So that helps me find A, which gives me 4. Now I need to find K, and we are given today that he can bench 200 pounds. Well, that means 3 years from when he started, which is today, he can bench 200 pounds. So we're going to use 3,200 to help me find K. So I divide both sides by 250, cross multiplied, subtracted 4 from both sides, divided by 16, natural log both sides, divided by -3 to get 0.925. And of course, store that in your calculator. So here's my logistic growth model for his bench pressing. And since I wanted to know how much he could bench press a year ago, that means I want to find P of 2. So I plugged in 2 for T and simplified to get 153.378 pounds. All right, now let's look at an example that deals with a table. So this table gives the number of yeast cells in a new laboratory culture, where T is in hours. Plot the data and use the data to estimate the carrying capacity for the yeast population. So if we plotted the data, we would get the following graph. And you should notice that the yeast cells are starting to level off at approximately 680. So I know it's kind of hard to use this graph to estimate that, but it's counting by 40s. So if you counted 40, 80, 120, and so on, you would get up to, this would be 680. All right, now we're going to use the data to estimate the initial relative growth rate. So, because I don't have too much information, I have this definition of the relative growth rate from a few topics ago, where K equals 1 over the initial times the rate. Now, in order to find the initial relative growth rate, that means I want it at the start. So I'm going to use these two starting points to help me find the growth rate. So I'm going to use my good old trusty slope formula for rate. So 39 minus 18 over 2 minus 0 will give me a rate of 10.5. And my starting population is 18. So that means my K, or the initial relative growth rate, is 0.5833. Now I'm going to write a logistic model for this data. So my carrying capacity is 680. I have my initial relative growth rate. I need to find A, so 680 minus my initial, which was 18, over the initial population, which gives me 36.7778. So make sure you store that in your calculator to get the following logistic model. Now we're going to use our logistic model to estimate the number of yeast cells after 7 hours. So I'm going to plug 7 in for T to get 419.818 cells. Hope you enjoyed learning about logistic growth, and I will see you in class tomorrow. Have a good night.